So we will define projectors BK and perform measurements, projective measurements, von Neumann measurements, and then we will get PK and rho K. And what is rho K? This is written in the previous slide. This. So after getting rho K, you can find S of rho K, and then you will get the conditional entropy. So for different values of different projectors one-dimensional BK, you will get the rho K, and there are many rows depending on the dimension, the number of Ks. So we will take the entropies of individual K and density matrix, and then we will take the average. So this we will take the average value. So this will give you conditional entropy. So this is conditional entropy, and if you put this in place of this thing, then you will define your mutual information, this mutual information, in terms of measurement operators. So now your mutual information is no more classical, rather it is dependent upon quantum measurement. So this is the formula for quantum mutual information. Okay, so now as you have calculated the quantum mutual information formula, then you have to optimize your mutual information. Why? Since depending upon the dimensionality of party B, you have different projective measurements, and you have to run over all the projective measurements. You have to run all the projective measurements on the row. So for that you need you will supremize the quantum mutual information. This is quantum mutual information, and if you take the quantum mutual information based on one-dimensional projectors, von Neumann measurement operators, then you have to ensure that you have made all kind of measurements. You have made all possible measurements in that dimension. So if you supremize or optimize your quantum mutual information, then this is called classical correlation. Classical correlation. So without classical correlation, it is mutual information, which is this thing. This is quantum mutual information without measurement. So this will ensure that total correlation. So quantum mutual information is total quantum information. So if you subtract the total quantum information from classical correlation, then this difference will give you quantum discord. So this is now the difference in quantum mutual information and supremized measurement quantum mutual information is called discord. So Q is quantum discord. Means you have total quantum information and you subtract classical correlations, because classical correlation is the information left in a system after performing the measurement. So if you perform the measurement, then the dependency of those states will be removed, and then only classical information will be left. Means in a quantum system there are two kinds of information: quantum information and classical information. So you have to, in I of rho, it possesses all the information, and minus C of P will give you classical correlation. C of rho will give you the information left after making measurement. So if you make the difference, so then this difference is called quantum discord. That is why this difference is called degree of quantumness. You are extracting the classical information from the total information, so you are left with the quantum information. So this quantum information or the quantum correlation is called quantum discord. So the degree of quantumness is inherent in Q of rho. So this is called quantum discord, and this formula is for asymmetric quantum discord, since you have only made a measurement on B party. Okay, and this is asymmetric just because of the fact that you are making measurement on second party, not on first party. You can define the same thing for first party, and you will end up with the same quantum information, but just this quantum information is asymmetric, although it quantifies the actual amount of quantum discord. Now that we have the formula for quantum discord, asymmetric quantum discord, so now we can apply this quantum discord for any arbitrary 2-qubit system. Let's say if we take a 2-qubit system, then you know that we can write a 2-qubit system in parameterized form, parametric density matrix. So this is a parametric density matrix form, and this is well-known formula for 2-qubit parametric density matrix, where these sigmas are Pauli matrices and gamma is the density matrix, and this is any arbitrary density matrix. Okay, so arbitrary density matrix with 4 by 4 matrix. This is a 4 by 4 matrix, and all of these entries in this density matrix is arbitrary. Okay, so if you calculate its discord, so then you will get the general formula for this discord. This is the general formula for discord, and the detailed calculation of this discord is written in my thesis. So if you have a density matrix, 2-qubit bipartite density matrix, and if those density matrix has got X structured form, what is X structured form? This is a class of density matrix in which the elements only exist in diagonal and off diagonal line. Okay, otherwise all of these are zeros. Here all the entries in the matrix is 0. So those density matrices whose form is X type, you can find the density matrix, you can find its discord by using this formula. Just what you have to do, you have to compare these coefficients C1, C2, C3 with your density matrix. So for density matrix with X state, X type density matrix, we will set these terms to be 0. So I have forgot to written over here. So just identity and this term will give you the X state X density matrix. So now that we have density matrix, so we can find the Werner state, and you know the Werner state is a kind of state omega, which is used to transform any pure state, pure quantum state to mixed quantum state, and from pure to mixed state you have to specify C. The value of C runs from 0 to 1. Here if you set C equals 1, 1 minus 1 is 0, 1 is this 1, this becomes 1, so you are left with the pure state. And if C is 0, then this term is 0, and you are left with 1 over 4 times identity. Now this is mixed state. So C here is the purity. So Werner state is a general state where you can write you can write Werner state for any pure matrix, pure quantum state. Let's say if you have any quantum state rho which is pure, so if you write its functional form over here, then this becomes the corresponding Werner state. And if you set the C, then it will change the values of purity, and by changing the values of purity you can see how the quantum discord behaves. Okay, you can even calculate its entanglement, and if you calculate the entanglement for different states and change the purity, then you will see that for C equals 1 means maximum impurity, means if C is 0 then this is called mixed state, and when C is 1 this is called pure state. So C is 1 means maximum purity, C is 0 means maximally mixed states. So Werner states are a model to transform a perfectly pure state into maximally mixed state. So for example, let's take Bell state. These are very famous 2-qubit states, Bell states, and these Bell states are, we know that, perfect maximally entangled states. So if we take the Bell state and find its quantum total information, so this is the total quantum information, and this is classical correlation for this, and this again, this calculation is done in my thesis in detail, step-by-step calculation is there. And if you subtract the total quantum information from total quantum information, if you subtract classical correlation, then you get quantum discord for Werner states. And if you set C equals let's say C equals 1, then you will get the quantum discord for Werner states with purity 1, means this will give you the quantum discord for Bell states. And this is the quantum mutual information C. Here the quantum mutual information has got maximum value 2, so I of rho is 2. And we know that from in quantum information theory, the entangled states, perfect entangled states for has quantum entanglement 1. The amount of quantum entanglement in them is 1, and even quantum discord is 1. So total quantum information is 2. So I of rho is 2, and classical correlation is 1. So how much is there the degree of quantumness? It's totally simple. You have to subtract these two and you will get 1. See, the quantum discord is 1 Bell states for Bell states, and quantum discord for Bell state is 1. This is calculated again in my thesis. Whereas from the past knowledge of quantum information theory, we know that the Bell state has entanglement, and entanglement for Bell state is again 1. See, for pure states, discord is equal to 1 and entanglement is equal to 1. And see, this quantum correlation is increasing with the value of C. So if the states are pure, maximally pure, discord is quantum correlation is 1. So quantum discord has a graph like this. So this graph is the subtraction of I versus C and classical correlation versus C. This has got maximum value 2 and this has got maximum value 1. So if you subtract 2 from 1, then you will get maximum value 1. That is why quantum discord for Werner state is 1. For Werner states where C is 1, and if C is 1, and then we know that this graph is for Bell state, so you will see the quantum discord in the Bell state is 1. So this is the same. So this is the Bell state, these two, this is Bell state, and you can write the outer product of this Bell state in the form of beta. So let's say this is beta. So if you calculate if you write the density matrix, then you will get 1 over 1 over 4 times I minus C, 1 minus C times I plus C times beta. This is the density matrix for Werner state corresponding to Bell state. And if you calculate the quantum mutual information, which is the total correlation 2, and if you have classical correlation, this is 1, and if you subtract both, you will get quantum discord. See, Bell state is perfect entangled states, so its discord is 1 as well as entanglement is 1, and it has half of its information is classical information, half of this correlation is classical correlation, and half of this is quantum correlation. So Bell state Bell state poses half of Bell state poses half classical correlation and half quantum correlation. So if as I told you, the entanglement has got value 1, so its concurrence gives you the value 1. Concurrence is a quantum correlation monotone for quantifying entanglement. So what is the analysis? For Bell state, concurrence and discord gives you the same result, means they are same. And classical and quantum information correlation are equally distributed for Bell state. C of rho is 1 and Q of rho is 1. Fine. So same for Bell state. And since concurrence is equal to 1, so Bell states are maximally entangled state and maximally discorded state, because discord of Bell state is also 1. So now that we have calculated the quantum discord formula and we have applied it for entangled states, Bell states, I just told you that in the previous derivation of discord there is an issue that this earlier proposed discord formalism is asymmetric, And not only this, but whenever you extend your system from bipartite to multipartite system, the system situation become puzzled because of non-unique generalization. So this has non-unique many generalization. If you follow the procedure that we have derived, we have written for asymmetric discord. So we are looking for a solution, a new alternative derivation definition of quantum discord, which is not only symmetric but unique. So the answer is given in the paper of Rulli, published in Physical Review A in 2011. So I also have derived this paper in the results of this paper in my thesis. So this newly proposed definition of discord is called global quantum discord. So global quantum discord is unique and symmetric. So some of its features are the following. Global quantum discord is based on quantum relative entropy, and quantum relative entropy is better quantifier of correlation, as this is based on distance based discord. Means it is based on the formula of quantum relative entropy, and quantum relative entropy is a kind of distance based entropy information, or entropy information entropy, which gives you the separation between two quantum correlations, or you can say the quantum states. So if the states are more separated, then discord is large. I mean, means if quantum relative entropy gives you the distance based discord, you can say. So global quantum discord allows us for the unique view of different quantum correlation monotones, as many successful quantum correlations monotones discovered and discussed earlier in the literature are based on quantum relative entropy. So this gives us a unified view of different correlation monotones. And quantum discord, global quantum discord, is obtained by systematic extension of bipartite quantum system, satisfying all the properties of standard quantum correlation monotone. So this is a good quantifier, a relatively better quantifier than the asymmetric quantum discord, as it satisfies all the criteria for a correlation monotone to be a quantum correlation monotone. So now let's discuss the mathematical formalism of global quantum discord. So for two qubit system, global quantum discord is defined in this way. First, you have to calculate the mutual information, quantum mutual information, and you have to calculate the quantum mutual information after making all possible projective measurements. Pi aj is for first party, pi a all the quantum measurement related with j means for first party is applied on the rho a of rho ab, and pi jb will apply on simultaneously applied on rho b of rho ab, and then you will get the quantum mutual information after projective measurements on both party, and then you have to subtract these information, quantum mutual information without projective measurement, von Neumann measurement, and quantum mutual information after projective measurement, and then you will subtract. This subtraction is called measurement induced disturbance, means what is the value of disturbance in the quantum information whenever the measurement is made. So this is called MID, measurement induced disturbance, and you have to ensure that your measurement is performed on all the states of the rho AB. So you have to minimize your system. So you will minimize on the system on all the J's. So then if after minimization you will get the discord for AB, and this discord is symmetric, where I of phi AB is defined in this way. Phi AB means you have to take rho AB and you have to make this quantum operation. This is the definition of quantum map, quantum operation. If you perform a measurement, this is the same formula which is discussed earlier, but the projectors are for both the parties. So let me show you the equation, which is the modified form of So where is, yes, this thing. So here we have, instead of this we have pi a cross pi b. These are the measurement operators applied on row AB, and this density matrix is sandwiched between pi b. Then you will get this thing. Okay, so this time you are making measurement. Instead of writing I, you are writing pi a. So this is the symmetric measurement. So measurement is performed on both parties simultaneously. So this is symmetric. So let me come back to the original point. So this thing. So this is the density matrix after von Neumann measurement on both parties. Okay, so now you have phi of AB. So if you have phi of AB, then you can find phi of A by taking the trace over B. Similarly, you can get phi of A by tracing over B, and then you will take the then you will find the cross product of rho A and rho B, and then you will calculate this conditional entropy. This is not conditional entropy, this is relative entropy. So this relative entropy without measurement give you I of AB, this thing, and after making measurement you will get phi of A, phi of B, and phi of AB. Then you will use this formula for phi's. So you will subtract, and since you will subtract your both informations, quantum information and total information, and then you will make measurement on both parties. So let me just come to the point. So this is the definition of discord. Okay, so this is the definition of discord, and when you generalize your global quantum discord for multipartite system, then you only have to make the tensor product, multiple tensor product for as many systems as you have. So you will get the projectors of those systems, and you will place all those projectors in the tensor product and sandwich your density matrix among this equation, and so the recipe is just flat. So this thing. So this is again the same formula for discord, but with the strings of array of projectors. Okay, so you have projectors, array of projectors, and tuples of projectors. You have to sandwich that density matrix among in between these projectors, and then you have to perform the same calculation. Then you will come up with the formula of the value of discord for n qubit global quantum discord, n qubit discord for those systems. So here I have taken the 3 qubit system, tripartite system, and I have taken the 3-dimensional version of Bell state, which is called GSE states after Green, Berger, Horny, Shimnoy, and Zeilinger. So this is a GSE state, which is the 3-dimensional version of Bell state, and I have made the Werner state with the general structure of Werner state. I have replaced the general density, pure density matrix by GSE state, and I have where GSE is this upstate for A, upstate for A plus upstate for A, so ABC, and downstate for ABC divided by 2. This is very much similar with the Bell state, where Bell state is 1 1 plus 0 0 divided by 2. So this is for 2 qubit and this is for 3 qubit. So for 3 qubit we define GSE state, which has the same property as Bell states, just its dimensionality is 3 by 3, whereas for 2 by 2 we have Bell state. So if you calculate its discord, you will get this result. And now this is Werner state based on GSE state. So you can change the value of purity. Here mu is the purity, maximum value is 1, minimum value is 0. So mu varies from 0 to 1. So if mu is 1, you will see this term goes to 0. So you will end up with GSE state. So mu equal to 1, Werner state turns into pure GSE state, and GSE states are Bell states. So we know already that the discord entanglement for GSE state is 1, and you have if you have put the value of mu equals 1, you will see the discord turns out to be 1. So here on x-axis we have purity, on y-axis we have discord for Werner states based GHZ state, and if you see, while increasing the value of mu, you are adding purity in the system, means mixedness is decreasing, purity is increasing. And if you set, and when you come to mu equals 1, this becomes perfectly pure states, which is GHZ state, and for GHZ state it gives the value 1. So the discord for GHZ state is 1, and from the previous literature on GHZ state we know that the entanglement for GHZ state is 1. And I also have calculated the GHZ state entanglement for GHZ states, which is 1 in my thesis. So this is the way we quantify global quantum discord.